x plus 3, x plus 2, x minus 1. So if you multiplied this out, you get the x times x is x squared, times x is x cubed, and so this degree is going to be 3. Now, we also notice that when it's in factored form, these factors are really useful to us, because if x plus 3 is a factor, we know that negative 3 is an x-intercept, because x plus 3 equals 0, so x equals negative 3 is a root. Negative 2 is also a root, and 1 is also a root. And so what we noticed was how those were connected to the graph. We could graph this, we could go over to negative 3, negative 2, and it went through 1, and your graph semi look like this, with the exception of it might be higher, it might be lower, but those are the points where it went through the x-axis. The problem comes into play is when you can't factor something, and so that's why we learned about division, because when you divide, you get factors. When you divide 12 by 2, you get another factor of 6. And so let's see another example. Let's take x to the 5th minus x to the 4th minus 7x cubed plus 7x squared plus 12x minus 12. So we have no method of even beginning to factor 6 terms. And so the first thing I say here is, well, let's sort of take this backwards. Let's go to the graph first, look for these x-intercepts. Those x-intercepts that we saw, negative 3, negative 2, and 1, and then we can go back and divide to find the leftover stuff. So go ahead and graph this. Grab your graphing calculator, plug all of this in. You may want to hit pause on the video, but what you notice that your x-intercepts look like they're going through negative 2 and 1 and 2 for sure. Now there's some that are in between and they kind of look like they're maybe 1.7, 1.8. But so what we're going to do is we're going to deal with this. If negative 2 is an x-intercept, we know x plus 2 is a factor. X minus 1 and x minus 2 is a factor. So what we're going to use is division. And I'm going to use synthetic division just because all of these are linear factors. So I'm going to use all the coefficients like we set up yesterday. So 1, negative 1, negative 7, 7, 12, negative 12. And what you want to remember for synthetic division is to include any zeros if you're missing any terms. Say if you're missing that x squared term, you'd want to include a 0 for it down here. Now let's just go in order from left to right, and it really doesn't matter what order you do it in, you'll get the same answer either way. But let's take our negative 2 first. And if negative 2 is a root, I put the root right here. Lots of times with the dividing by x plus 2, you notice that we changed the sign when we went from x plus 2 to negative 2. Still the case, but when negative 2 is your x-intercept or your root, that's what goes there. So let's drop down the 1. 1 times negative 2, negative 2. Negative 1 plus negative 2 makes negative 3. Negative 3 times negative 2 is positive 6. Negative 7 plus 6 is negative 1. Negative 1 times negative 2, positive 2. We get 9, negative 18. We add again. We get negative 6. Then we get positive 12. Now this is a good sign because when we add these we get 0. If you remember, that's our remainder. And if in fact negative 2 is a root, or if in fact x plus 2 is a factor, we should get a remainder of 0. Now you may want to go back and double check your graph. It may not have gone through negative 2 if you don't actually get 0. But so now we can say negative 2 is in fact a root. So what we're going to do is just continue our synthetic division. And so I'm going to draw another synthetic division. We're going to leave the 0 off of it. Because what's helpful is if you can take it, we just divided and got x to the 5th to become x to the 4th. And if we can divide again using our next 0, 1 up here, we can make it even smaller. We get 1. If we drop down the 1, 1 times 1 is 1. Negative 3 plus 1, negative 2. Negative 2 times 1 is negative 2. Add them together, you get negative 3. Multiply again, you get negative 3. Negative 3 times 1. Add them together, you get 6. 6 times 1 is 6. And you get 0. Alright, so 0 again is a remainder, so we know 1 is a root. So let's do it again. Just continuing our synthetic division. So this time, let's use the 2. That's the only one we haven't used yet. So drop down the 1. 1 times 2 is 2. Negative 2, so we get 0. 0 times 2 is 0. Negative 3 plus 0 is negative 3. Negative 3 times 2, negative 6. Add them together, you get 0. So again, 0 is our remainder. Now, so we just confirmed again that all 3 of those were roots. Negative 2, 1, and positive 2. These leftovers, if you remember this, negative 3 is our constant. We just divided by x 3 times, so it took it from being a degree 5. When we divided the first time, we got degree 4. Then we got degree 3. And now we got degree 2. And so this is our constant, this is our x term, and this is our x squared term. And so we're left with x squared plus 0x minus 3. So now what we can do is we can set the rest equal to 0. To find our other x-intercepts. So if we set it equal to 0, add 3x squared equals 3, take the square root of both sides. Every time we take the square root of both sides, we have to remember to add the plus or minus in there. Plus or minus square root of 3. So that's where our approximately 1.7 came from. So if we notice now, if we just sort of wrap this up, there's several things we can do. We can write all the x-intercepts, or the solutions, or the roots. And those we confirmed with synthetic division were negative 2, and 1, and 2, and positive root 3, and negative root 3. And then, if negative 2 is a root, we knew that x plus 2 was a factor. If 1 was a root, we knew that x minus 1 was a factor. If 2 was a root, x minus 2 was a factor. Root 3, x minus root 3, and x plus root 3. So what's really nice about this is that this is completely factored form of our polynomial that we started with at the beginning. We know what our x-intercepts are. We can find the exact values. That's going to be important. And so what we can also find is that sometimes your double roots for the fundamental theorem of algebra are going to be counted twice. So let's see, we had seen that signature bounce at the x-axis when x was 1. Then we could have divided by 1 twice to get it smaller still. Let's look at another